All right, the purpose of this video is to walk through the Planetary Nebula lab. Let's begin by going to the module and scrolling down until we find the Planetary Nebula lab. There are two files here that we need to download, and then there are the questions. That's where we will upload our completed Excel file and also answer the questions. The first one we need to download is the template file. So let's click on that, open in a new window. And when it loads, up here at the upper right-hand corner is the download button. And I'm going to download that to my downloads directory. Then I'm going to go back to the module and I'm going to download the Excel file, the data file. Click here on download, and that will also download to my downloads directory. I'm going to open both of these together, the template file and the data file, and I'm going to keep them side by side on my desktop. You can see here I have the template file and I also have the data file. I am going to enable editing on the data file. And it looks like on the data file, I have something called table 06.01 and data table 06.01. So the data table and the table are different. Keep that in mind. All right, let's go through the template then. The purpose of this laboratory activity is to determine the age of planetary nebulae using astronomical research methods and data gathered from stellarium. Here are the things you're going to need. You're going to need stellarium, you're going to need Excel, you're going to need the template file, which is the file we're looking at right now. We're going to need the data file, which we have open behind this. And we're going to need the questions so that we can answer the follow-up questions and also upload our data file. All right, now the background information tells you a lot of interesting information about planetary nebulae and what they are. And then it begins going into some math, and I highly recommend that you read this through. If you have any questions, please ask. There are two main equations that you will need here. This one right here, S equals R theta divided by 206265. That's called equation 1. For an expanding planetary nebula, there's a central star, usually a white dwarf, and we can determine how long the nebula has been expanding if we know the distance d that's drawn here, and we know how quickly it is expanding. Now that distance d, we can determine, make estimates on it based upon how far away it is, and the velocity v at which it is expanding is something that we can determine spectroscopically by measuring the radial velocity. Now here is the other equation that becomes important in this lab. This is labeled equation 2, and you notice the S pops up here in this equation. So the T is the age of the planetary nebula. The S we calculated using the previous equation, and then V is the radial velocity which we have to be given. So I go back up here and I look at S. There is R, which is distance to the object. Theta, that is the angular measurement of the object. How big does it appear in units of arc seconds? And then S is the arc length, which would be the physical diameter of the planetary nebula. So R is distance, theta is angular measurement, and 206265, that's a necessary multiplication factor. We're dividing by it in order to make the units work out correctly. Okay, but once we've calculated S, then we plug it in down here. You see you divide it by 2, and then you divide that answer by the radial velocity, and that will tell us the time. Okay, now the instructions here step through the process of determining that, but we're going to do that here and now. Now here is table 06.01. And you can see it contains a lot of information about the planetary nebula. Here's the catalog number of the planetary nebula. Here's the proper name of the planetary nebula. And then the distance to the planetary nebula in light years, and then the radial velocity. So we are given the radial velocity in units of kilometers per second. The distance is in units of light years. Now those are two different distance units. Light year is a distance and kilometer is a distance. So those two units need to be converted, and that's what the 206265 number does. And we may have to do a little bit of that as well as we go through this. So it says, don't confuse your tables. Data table 06.01 is not the same as table 06.01, and we can see that in our Excel file. Okay, here are the procedures, the instructions. We're going to step through that, but I'm going to go past it right now and look here at the data table. You can see the first one is filled in for you. We will go through the process of where those numbers came from. And then here are the others. Distance needs to be entered in kilometers. The stellarium angular diameter, that is something that we'll look up in stellarium, and it needs to be in units of arc seconds. The physical diameter in kilometers, we will need to compute that. The age in seconds, we will need to compute that. And then once we've got the age in seconds, we will have to divide by the right numbers in order to get the age in years. And you can see this one right here is 1.83 times 10 to the 4th years. So this would be 18,300 years. All right, and then we have some questions. Look like we have 5 questions here. Which of the planetary nebula is the oldest? Which is the youngest? What are some things happening on Earth around the time that one began expanding? And what are some of the possible errors? And why do you think all planetary nebulae, not just the ones in this lab, have ages not much greater than 50,000 years or so? All right, well, let's go back up to the procedure and begin the process. First of all, it says inspect this table here, and we have already done that. So step 2 is convert each distance displayed in table 06.01 into units of kilometers. So the first blank in the data table is this one right here. For the ring nebula, which is M57, we need to enter in the distance in kilometers. We are given the distance up here in units of light years, so we need to convert light years into kilometers. And the procedure will help us do that. Convert each distance displayed in table 06.01 into units of kilometers and record the values in data table 0601. To convert light years to kilometers, multiply distance in light years by this number right here, 9.461 times 10 to the 12th kilometers per light year. And then since this is a lab that's going to involve the use of scientific notation, there is a note here that says expressing scientific notation in Excel is a little different. For example, the mass of a proton, which is 1.67 times 10 to the negative 27th, would be entered into Excel as 1.67 and then E minus 27. The E is the times 10 to the. That's what you can think of the E meaning, times 10 to the. All right, so I would read this as 1.67 times 10 to the negative 27. And then here's another example. The speed of light is 300 million meters per second. That's 3 times 10 to the 8th, which is 3e plus 8. All right, so for our example here, we need to take this 2871 and we need to multiply it by 9.461 times 10 to the 12th. Let me show you the easiest way to do that, I think. Equals 9.461 E 12. And let's go ahead and enter the plus 12. So I entered 9.461 E plus 12, and now I need to multiply that. So I'll put star this cell right here, that one right there. Now I'm going to hit enter. And you can see the answer is 2.71625 E plus 16. Let's go back. Let's see if that's what the answer is here in the procedure. For example, the ring nebula to be at a distance of 2871 light years, multiply this by 9.461 times 10 to the 12th kilometers per light year to determine the distance to the ring nebula in units of kilometers. And when you do this conversion, you will find the answer is 2.716 times 10 to the 16 kilometers. Or if we write that out, you can see it's 2.716 E plus 16. Now, 2.716 E plus 16. Let's go back. 2.716 E plus 16. You can see there's some extra decimal places in there, but that's it. We can adjust those decimal places if we want to, like that. All right, now we need to do exactly that same sort of thing for all of these distances here. And if you do that, you can copy this formula and just paste the formula in each one of these. All right, we've finished with that portion. Now let's go to step number 3. In Stellarium, use the search function to look up each planetary nebula and find the angular diameter of each. Now this is something that we have to look up for each one. Let's go to Stellarium. There are some notes here. For the Ring Nebula, Stellarium shows the size of 0 degrees, 3 minutes, 48 seconds by 0 degrees, 2 minutes, 24 seconds. That means that the nebula is a little bit longer in one direction than it is the other direction. So it's not circular in the sense that it's not a perfect circle here. So it's a little bit wider than it is taller, perhaps. Since the first angular diameter is larger than the second, the first will be used. Now, what we need to do here is we need to always use the larger of the numbers. So here we've got 3 minutes, 48 seconds or 2 minutes, 24 seconds. Well, obviously, 3 minutes, 48 seconds is bigger. So what we need to do is we need to convert that into angular diameter in arc seconds. So 3 minutes that's shown right there, remember there are 60 seconds per minute. So 60 times 3 plus this 48, that's what we will need to enter in, okay? So 60 times 3 plus 48. Now we need to actually look this up in Stellarium. We probably shouldn't trust what the procedure says. So let's go and look it up and confirm that that's the case. So I'm going to start Stellarium now. When Stellarium pops up, I'm going to get rid of the atmosphere and the ground and the cardinal points. And I'm going to search for M57. When I hit enter, it puts M57 right here in the center. And if I zoom in, there's the Ring Nebula. And you can see it's a little bit wider one direction than it is the other directions. So that's why it has 2 different angular diameters for its size. I'm going to go into Windows mode here so that I can put that right in front of you. And you can see there's the nebula, and then over here we need to look for the size, the angular size. And you can see it's right here. This is the 3 minutes 48 seconds by 2 minutes 24 seconds. So what is here in Stellarium is exactly what was in the procedure. But if we didn't have these values already in the procedure, we would go with 3 minutes 48 seconds. So 3 minutes 48 seconds, I'm going back here. I need to plug in the diameter. Now, I need to do this 3 times 60 plus 48. So that's 3 minutes. I have to multiply by 60 to convert that to seconds, and then I add the 48 seconds there. So when I do that, I get an answer of 228. So let's go back to the procedure and see if that's what they got. Since the first angular diameter is larger than the second, the first will be used. When converted to arc seconds, 3 minutes 48 seconds becomes 228 seconds, okay? And that is exactly the number that we got. This is the number that's recorded in the angular diameter table. So that should be 228, which it is. Now you have to be careful here. Whereas you could paste the formulas here in the distance column because you're just getting the next one here and pasting it down, you can't do that here. This is actually a calculation that's performed to find that 228, and you can see it was 3 times 60 plus 48. Each one of these nebulae is going to have a different size, so you're going to have to do each one individually. Okay, moving on to step number 4. The next step is to compute the physical diameter S of each planetary nebula using equation 1. Let me remind you what equation 1 was. This is equation 1 right here, so we're going to compute S. Scrolling back down here to this, to step 4 again, compute the physical diameter S of each planetary nebula using equation 1 and record these values in data table 1. If you're using the values of data table 0601 as your input and you have properly converted all values, then the physical diameter will be expressed in kilometers. These values will be large, so you will once again want to express them using scientific notation. Now, R is the distance to the nebula in kilometers. That's the 2716 times 10 to the 16th that we got. That's this number back here, so that's the distance. That's R. And then this is the angular diameter in seconds of arc. Let me remind you one more time what that equation is. So R is the distance to the nebula. This is us back here at the tip, and we're looking at the nebula off in the distance. R is the distance to the nebula, and theta is the angular size of the nebula. And then S would be the actual arc length, the actual size of the nebula itself, its physical size in units of kilometers. That would be its diameter, actually. All right, so this column right here, the distance in kilometers, that is R. This is theta, and we need to compute S. S will go right here in this column. So S is equal to that multiplied by that divided by 206,265. And I hit return. And the answer is that I got is 3.00 times 10 to the positive 13th. Let's go back here and look and see what they got. S equals 3.00 times 10 to the 13th kilometers. So the physical diameter, the actual diameter of this nebula, M57, is 3 times 10 to the 13th kilometers. That's very large. Okay, step 5, we're now ready to compute the age of the planetary nebula. We're going to record that in the data table, and we're going to need to utilize for this calculation the radial velocity from that first table, table 0601, as part of the calculation. Now the age that we're going to compute is the age in seconds, so we're going to have to convert that, and we'll do that in the next step. So we need to use equation 2 for this. Let me remind you what equation 2 was. It's this one right here. The S is the value that we just computed, and you notice that it's S divided by 2. That's because S is diameter, and what we really need is the radius. Divide that by the radial velocity, and that will tell us the time that the nebula has been expanding in units of seconds. So take the S value, divide it by 2, and then divide that by the radial velocity. So here I am, planetary nebula age in seconds equals S, that's this, divided by 2, and then I need to divide that by the radial velocity, which for the Ring Nebula is this one right here. And I got 5.77 times 10 to the 11th. Let's see if that matches what is in the procedure. And 5.77 times 5.77 E plus 11 right there. You can see that right there. Whoops, right there. Okay, so the next step then is to convert that, which is in units of seconds, to units of years, so we can figure out how many years has it been expanding. All right, so here we are. We want equals this value right here, which is in units of seconds, and we need to divide by 60. That converts it into minutes, and then divide by 60 one more time. That converts it from minutes into hours, and then divide by 24. That converts it from hours into days, and then divide by 365.25, and that converts it from days into years. Let's see what we get. 18,297. Great. So is that what the procedure tells us? Yes, 18,297 is exactly what they got. So there's your answer. So 18,297, that means that the Ring Nebula, the star at the center of the Ring Nebula began to expand and lose its outer shell of atmosphere about 18,297 years ago. And it's been expanding ever since. Now, this assumes that the expansion has been at a continuous rate, which it may not have been, but this means that this is the approximate age of the Ring Nebula, 18,297. Okay, and that is the procedure. That you will need to do that for all of the other nebula that are listed here. So the Eskimo Nebula, if I were to go to Stellarium and I were to search for the Eskimo Nebula, let's see, what was its designation? NGC 2392. I may also be able to search for the Eskimo Nebula, so let's see if I can do that. Okay, so there's the Eskimo Nebula, and if you zoom in, there it is. Central star and an expanding shell of gas around it. And when I zoom out, I can see its size is 48 seconds by 44.82 seconds. So 48 is the larger, so I would use 48 for the size here. Okay, and that should help you moving forward then. The stellarium angular diameter for that one is going to be of that size, 48. All right. Then just follow the procedure once again and fill in all of the other blanks here, and that's it. Answer the questions. If you go look at the questions first, you'll discover that they're all multiple choice, and that should give you some idea as to what the answers should look like. And then as the very first question, actually it's called question 0, that's where you will upload your finished Excel file. Be sure you save your Excel file to a folder where you know where it's at. Be sure you check it before you upload it, just to make sure. And if you need to retake it because perhaps you think you made a mistake on the questions, or maybe you uploaded the wrong file, you need to make sure that you complete all of the questions and the upload each time you retake the quiz. All right, that's it. We are finished with the Planetary Nebula Lab. If you have questions, that's what I'm here for. So ask away. And that's it. See you online. Have a great week.